Okay, here are solutions to the activity on continuity from section 1.8. I've written most of these out already, and we'll try to walk through them. The first question says, for each function below, state all intervals on which the function is continuous. The function has a discontinuity, state what kind. Okay, so here we're looking at some rational functions in the first three examples, and those discontinuities are going to occur if the denominator is equal to 0. In this first example, x squared plus 1 is actually always positive, hence will never be equal to 0, and so our function is continuous on all real numbers, or from negative infinity to infinity. In the second example, the denominator x plus 1 will equal 0 only once when x is equal to negative 1. Also, since we can't factor it out of the numerator, x equals 1 then becomes an infinite discontinuity, and the function is continuous on the interval from negative infinity to negative 1, union or and, in case you haven't seen that symbol before. This symbol stands for and, the interval from negative 1 to infinity. Okay, another 0 in the denominator in the third example here happens at negative 3. However, h of x can be factored as x plus 3 times x minus 3, so we can in essence factor out that thing that's causing the discontinuity. When that occurs, we get the graph that looks like a line, in this case x minus 3 with a hole in it, and so we have a removable discontinuity at x equals negative 3. And the function is continuous everywhere except negative 3. Another way to write this could be all real numbers except x equals negative 3 would be acceptable as well. Okay, this function j of x, let's think about what happens. Well, it's definitely not defined at 2. If I take an input larger than 2, like j of 3, that's going to be the absolute value of 3 minus 2 over 3 minus 2. But those things are positive, both of them, so that's just going to be 1, and we'll always get 1 no matter what that output is. But if I take something smaller than 2, like say 0, I get the absolute value of 0 minus 2 over 0 minus 2. Well, the absolute value of negative 2 is 2, but I still have a negative in the denominator, so this is negative 1. So here, the graph of this looks like a straight line 1 for x's that are greater than 2, and a horizontal line at negative 1 when x is less than 2. And we have a jump discontinuity. At x equals 2. And now go ahead and write out the interval on which this function is continuous. It should look very much like the one above, except where you see a negative 3, replace it with a positive 2. Okay, number 2 says, use the graph below to illustrate the intermediate value theorem for x squared on the interval from 1 to 3. Okay, so f of x equals x squared is continuous everywhere because it's a polynomial, so it's certainly continuous on the interval from 1 to 3. F of 1 is in fact 1, so there is f of 1, and f of 3 is not 5. I do not know why that is there. Let's fix that. F of 3, we can handle 3 squared. F of 3 is 9. There it is. F of 3. Okay, and where does 5 live in between 1 and 9? Yes, it does. 1 is less than 5 is less than 9. So the intermediate value theorem says that f of c, there's some input that gives 5 as an output for c in the interval from 1 to 3. If we draw that line over at 5 and we come down here, we see that c lives somewhere just slightly larger than 2 in this case. Okay, number 3. Show that x cubed minus 5x plus 1 equals 0 has 3 solutions between negative 4 and 4. Sorry, x cubed minus 15x plus 1. So we want to show, in essence, another way to think about this is that x cubed minus 15x plus 1 crosses the x-axis 3 times between -4 and 4. Well, what do we know about this? X cubed minus 15x plus 1. It's a polynomial, so it's continuous everywhere. So it's certainly continuous, spelled incorrectly, on the interval from -4 to 4. Okay, that means every time it switches, the outputs switch from negative to positive, what's going to have to happen? Well, if our function has some negative output and it switches to some positive output, in between there, because it's continuous, it will have to cross the x-axis or have a root. So really the question is, how often do the outputs of x cubed minus 15x plus 1 switch from negative to positive? Okay, so I created a table of values, and we'll just make a mark here. We'll draw a line every time outputs switch from negative to positive or from positive to negative, and that happens 1, 2, 3 times here. So the intermediate value theorem gives solutions to x cubed minus 15x plus 1 equals 0 in each of the following intervals. Well, we switch from -4 to -3, so there's a solution in that interval. We switch from 0 to 1, so there's a solution in the interval from 0 to 1. And finally, we switch from 3 to 4. So there's a solution somewhere in the interval from 3 to 4. Of course, it doesn't tell us what those solutions are. It just narrows down where they might live. And if we narrowed our inputs down and looked at smaller intervals, we could narrow down where the solutions occurred.